Hey everybody, Dave Lindbergh in Hong Kong with another episode of the THD Podcast. Our website is live now, so everybody can go to totalharmonicdiscussion.com and check out what's been going on. And today's guest is a company out of Irvine, California named Syntiant that does a neural decision processor, so we're going to find out about that. But as always, our co-host in Sendai, Japan, Mr. Simon Weston. How are you doing today, Simon?
Really good today, Dave. We're
Really
talking
good.
wake words, I think, aren't we?
Wake words, and wake word on the edge is kind of like what it's all about. So Mr. Dave Garrett in
edge.
Irvine, California. How are you doing today, Dave?
Hey, doing really well. How yourself?
Doing well, thank you. So yeah, Syntiant's been kind of bubbling under for a little while. The concept of talking to your devices has been around for a little while, but then talking to battery-powered devices has been a challenge because of what the processors that are available to be listening that are out there. So maybe we could start a bit with an introduction on Syntiant to find out what it is that they're offering for this audio market.
Yeah, no, and I think that's an awesome. So I'll share a set of slides. My name's Dave Garrett. I'm a VP of hardware at Syntiant. So, my teams, we build the silicon, that forms the core of the Syntiant solution. So we'll walk through the company, and then we can take a deep dive into a couple of the chips that we have available.
Sure.
So the idea behind Syntiant, really, it's more like the intelligence of things instead of the Internet of Things. So, I think the basic premise is AI is so good at so many domains. And what we're trying to do is just put substantial amount of AI at the edge. So instead of, dumb devices and just connecting things, we're trying to put significant compute at the edge and do that without affecting your battery life and without affecting, the ability for you to run billions of these little endpoints out there.
Okay.
There's all kinds of things. Why do I want to compute at the edge? And, the cloud has taken over the last, say, 20 years. And you say, hey, I can just put everything in the cloud. Everything can be done in the cloud. Well, there's a couple of things that you look at. We say, first off, privacy. Do you really want all of your data wrapping up to the cloud? So with processing at the edge, we're trying not to move those things around in the internet. We can intercept that. We can wait for words to be said and then not be, always listening, but not always forwarding your conversations.
Right.
We have the reliability and responsiveness too. I don't know if your viewers have seen this privacy issue, but it seems a big deal right now.
Mm-hmm.
And then, of course, obviously, battery life. Anytime you want to move into a mobile device, we only have a certain amount of energy. You can't carry around that much energy. The battery technology hasn't changed all that much since say the last 10 years. It's a relatively flat curve, and we're trying to put more and more processing at the edge.
Right. Okay.
So, this is a background Syntiant. At this point now, we're over 70 employees. It's a pretty neat company. So the median experience is over 20 years in the semiconductor space. Anyone knows about statistics, mean, average, whatever. The median means we have a lot of very experienced people. And then on top of that, we have a lot of very good, smart junior engineers that we can guide. And that's the strategy behind startups. Is you usually need people that have, attempted and failed at things, worked at big companies, understand the processes, yet now understand how to move quickly and move agilely in a startup. So I think we've got this great mix of pretty seasoned experts and then, the raw horsepower from the ML and the software teams to go attack these problems.
Okay.
Key investors, we got some, pretty good people on our cap table here. So Intel Capital and Microsoft Venture Fund, Amazon Alexa Fund and Bosch, and there's some pretty good names and big support for us, behind those names.
Yeah, at Atlantic Bridge, they came in the last round.
Yeah, and we just closed our Series C, last year in 2020, and Atlantic Bridge is a financial VC, so that's also a good indication. So people also interested in the company.
Right. Okay.
Applied Materials also in Bosch. Bosch from the sensor side, and Applied Materials is just they move so much of the semiconductor world. So these are big help.
Yeah, key allies.
Yeah, yeah. I mean, the good news about Syntiant is, we had our first production orders. So the company's been around since 2017. I mean, orders were 2019. So I think in the semiconductor space, I haven't seen it
Yeah.
done faster. Maybe it's out there. I'm not sure.
That's outrageously fast, to be honest.
Right.
Yeah.
And so, we crossed from production orders. I mean, we just in January this year, we shipped 10 million units. And so, at this point, AI, ML at the edge. I think we've got to have the total shipments. We've got to probably have the record at this point.
Okay.
And, we're pretty excited about that. Picked up lots of awards. It's been a crazy 3-year run.
Yeah. All right.
A couple of things in 2021. We already touched on the 10 million units shipped. We crossed that right in January. We've been, the reason we're discussing today, we've just kicked off our new chipset, the NDP120, and so that's we'll talk about a lot near the end of this call. We've already gotten picked up a CES Innovation Award in 2021 for that part, and that just extends our record for 2 years in a row. Our previous part, we had CES Award last year as well.
Yep.
So exciting. So we talk about, the user interface, and, voice and audio has really kind of taken this huge upswing as of late. And, we kind of look at the interface like, why is voice important? When you chart how we've interacted with our compute machines, you go way back, I don't know if you've ever touched one of these old IBM machines, but, it's the keyboard was this, I could teletype keyboard is how I interface with my computer.
Yeah.
And then at some point we moved into the mouse. It's all of a sudden this additional pointing device, and you're like, oh my God, it's graphics, and it bought this new angle.
Yeah.
The touch screen shows up, and next thing you know, you swipe your screen and things like that. But what we've really, really seen lately is intelligent voice is what's taking over, and everybody is going to interact with. Voice is going to be your primary interface.
Yeah, and it seems like the acceleration of the adoption of a new UI it's just like a hockey stick, because touch came out in 78 with ELO was I think the first guys to do it with resistive touch, and
Right.
It took a long time to become commoditized. But intelligent voice is literally I don't know when do we know when that first came out, intelligent voice, and now it's commoditized?
Yeah, it hasn't been all that long, I tell you. It probably done early, but not done well.
Right.
There's an Echo and there's a Siri in everyone's hands today, and you can talk to your Google, Android phones. It's really just ubiquitous.
Right.
And kids these days, that's the foundation of Syntiant. Is Kurt was watching his kids interact with their devices with voice, and voice chat and voice, even text. Like, I don't even want to type out a text. I'll say it to my phone.
Yeah. And I noticed the Google is so much better than the Apple in terms of the text to voice to text recognition, and that's to do with libraries, and I'm sure we're going to get into that a bit later here.
Machine learning is all about training data. So if you have billions of instances, that's an advantage.
Cool.
And like to walk through intelligent voice, we're kind of going through a same kind of scale as. At the low end, when we think of AI at the edge, we can look at sensors and events and wake words, but then you start moving up. I'm not just waiting for a single word, I'm waiting for command words. So you string together, some wake up, and then, hey, an action. Do I want volume up, volume down? That's our evolution of thinking of voice as an interface.
Yeah, and that's really kind of, for our audience, putting that voice control onto true wireless stereo earbuds, really low power things that you can talk to, but then talk to in noisy environments, like on the metro system here in Hong Kong. Are you going to be able to hear that? And so that's where the real fancy technology comes out, to be able to distinguish with a heavy noise floor.
Right. Yeah, absolutely. And like, honestly, with my earbuds, do I have to tap 3 times to reject a call or whatever? I never can remember the the command sequence. Like, I don't know, 3 taps. Does that make sense to me? Probably you could learn it, but in much more natural language. Hey, let's figure out how to talk to these devices. It's really kind of changing the game.
Cool.
But, as you move up in neural compute, there's all kinds of things that, we're going to be able to fit into an earbud, a TWS earbud. I mean, speaker identification. Let's not just let, anyone say these words. Let's make sure we know who's allowed to say these. Speaker validation.
Right.
The holy grail, and, this is along our trajectory. Conversational speech is let's think even more natural. Let's not form a command and a word, and let's people have conversational speech. So certainly that's on our evolution as a company to really be, at all levels. So what power you're willing to spend, that'll give the performance that we're allowed to attack.
Okay.
But again, preaching to the choir. I think you guys are already bought in voice, so this is good stuff. We Syntiant markets. I mean, we're attacking in design wins and design ins all over the place. But we have kind of, if you look at the two columns on the mobile side, I mean, we're in feature phones and smartphones. And, there's some pretty cool things where, just not draining the battery, allowing Syntiant to be the front end gateway for wake words is pretty powerful. We're even in laptops, to provide some voice interface. The IoT side is the interesting part as well. It's because where the volume is really, really high is wearables and earbuds are these great opportunity.
Yeah.
The virtual what's that? Yeah, connected home.
Like light bulbs.
Right.
Like eliminate the light switch, the amount of copper you'd save in the wall if you could just say on and off. I mean, it's incredible.
Yeah. That's right. And, you built these little earbuds, you're surprised how much these buttons cost. And then, even, putting a cap on an earbud with a capacitive touch wire is another, switch that has to go into the form factor. So getting rid of all of those little things on all of the devices in your home are just add up. It adds up for savings.
Right. Okay.
But I mean, again, you can see always on deep learning. That's a strategy for battery powered devices. I mean, we're trying to give you this compute that exists and do it in such a way that it's going to enable the use cases. I couldn't possibly put this compute before because it wasn't efficient enough. And so, we try and drive power down. The next thing you know, if you have a power budget, maybe we can give you 10x the compute. You all of a sudden build a form factor or a use case which is more powerful.
Right. Yeah, and like the use cases are quite varied too. I mean, just living over in Asia here, there's always a security guard in the building, and you just think of the classic sleeping security guard. But for industrial IoT, there's a lot of sensors that can go into things to detect and with the learning, it can go, is that a window breaking or not? That's kind of a classic thing. And also, like another one was a gunshot, to detect a gunshot. Yeah. And so all these things in kind of police force and security force for the industrial section is pretty powerful.
Yeah, absolutely. And again, I tell you that, you touched on that. So, the great thing about machine learning, right, is it's just this new way to think about attacking problems. And, going to the academic papers, I mean, there's 20, 30 years of research on how to look at, analyze voice and find words and all these traditional methods. And in, the span of 5 years, machine learning has just upended all of the results, invested every single result by some, master student could train a network to do better than what somebody used to have their specialty. And, that's kind of how we structure our solutions in our company is we really think of, 3 pillars of deep learning, and it's not just having the best silicon. So that's the way we can lock in, our inference at the edge. But at the same time, we actually have to deal with, the pipeline and the data. So we train, words for customers. We have the ability to go acquire, the 50,000 utterances in the dialects and the language that you need and feed that into our machine learning pipelines. So, it's not just that easy to go build production machine learning solutions, because you really are doing all kinds of really cool stuff behind the scenes where we'll train words with augmentation, like, reverb of rooms. And we can add, NPR News is one of the, the things when you go for Alexa certification. So we can train with, radio noise, and you could go into Hong Kong and train with the background noise of the train. And now you've taught this machine learning thing to listen and understand, oh, okay, this is noisy. This is what a train sounds like, but this is still the words I'm looking for.
Right. Yeah. It's all about that data to be accurate.
Right. So, again, there's providers that you can just get inference at the edge, but as long as you don't have the data or the pipeline or the solutions to do that, and, we try and put all three under the same banner. And, that's what you can do as a startup. We don't get these silos that separate, the domains. And it really gets us a chance for our silicon hardware engineers to talk with our ML team and collaborate on these three platforms.
Okay.
So, yeah, I mean, this is, the first product that went out, the NDP100. 10 million units out the door now. And it's, you look at the block diagram, it's really not all that complicated of a chip, right? The idea behind it is as quick as we can, we get audio from, a microphone or an I2S interface. And we quickly get that into feature extraction. And so this is a way to compress the information. So we're looking at, log melbins, analysis of audio, but really the goal is to dump this into this deep neural network. And that's it. The chip is building a 500,000 parameter neural network, and the idea is train that to look for wake words and command words. And it's interesting in that our job is to intercept almost all of that and let the system think that nothing's happening, go to sleep, and let us fire an interrupt and say, hey, you know what? Now I'm pretty confident something significant has happened and you should take a look at it.
So is there a way to simplify like the deep neural network so people understand that, like, say there's a vowel or some kind of element of a noise that's created passing through this, and it's trying to verify, is that a yes, no? So there's a logic going on there. And is it a culmination? It's like, say you utter the word Alexa. Is it a culmination of all those elements of the word that it defines through this TensorFlow type ML learning stuff?
No, it's an interesting question. And like phonemes, like people, like all these language recognition, you try and break things down into individual sounds. Mm-hmm. Here is the magic of machine learning. We don't care or don't know honestly what's happening on some of these internal nodes of this neural network. Is we hammer this network in training with millions and millions of utterances of the word Alexa, and we ask it at the end and say, you know what, this was Alexa, this is not Alexa, over and over again. We just train this thing, and in the end the machine is finding the patterns. And, it's not saying, it's an A and there's an X, and, it's not doing that. It really is finding some bizarre structures out of all of the noise and all the reverb and everything that you hammer. It's finding the word. And that's the magic. It's actually doing a better job than you and I could ever, do by trying to sit down and analyze it on paper.
So is that kind of the core difference between an NDP processor and a microcontroller-based wake word system? As I understand, the microcontrollers are comparing their library of utterances. So if you say Alexa, it will go and compare to that library, and that costs a lot of power to do that. And so your words are just flowing through your network, and it comes out with the decision at the end, without having to do that reference back and forth to memory. Is that I'm trying to condense what the power savings is coming from.
Yeah, again, so it's a custom architecture. This deep neural network really doesn't load programs. You can't go run arbitrary C code on it. It is really just dedicated for attacking machine learning. And so the main difference you'd say between us and, say, a microcontroller is just the sheer amount of compute that we can put towards neural. So we can put 500,000 parameter network on this device, and it allows us to do exactly that, train these types of networks. And, we've put this device through Alexa certification for close talk. So, that's a pretty tough spec. And it says, you have to pass something like 3 false accepts in 24 hours. So there's background noise and things like that. You're not allowed to classify a word more than 3 times. That's a tough thing to do. There's a lot of the front end voice networks have a permissive front end. So they have an MCU, and it's kind of very small. It's a small neural network, and it wakes up. It false accepts a lot. Not all the time, but it's really permissive. And what happens is you have up with a second stage, and you have to cascade these solutions. Our goal is to say, let's throw as much power as we can as early as possible, and make sure that when we tell you something, it's actually what's happening.
Okay.
But you can see, look at it. I mean, that's the device. That's the picture on the top right. I mean, that is
It's tiny.
we have our famous picture with Abe's beard on a penny. I mean, it's 1.4 by 1.8. So, I mean, there's not a place that we can't drop this device into. It's on the margins of a SoC, and there's sometimes decoupling that's bigger than our device.
Yeah. So just the reference there for everybody, that's Abe Lincoln on the American penny. There's a picture if you go to the Syntiant website, everybody.
That's right. Yeah, that's right. And again, what comes with this is just an enormous power advantage. The density of our solution, and we're winning on all of power, cost, and the form factor. It's been really an outstanding, crazy thing. And what we look at is, like I said, always on power, running this 500,000 parameter neural network, all in 140 microwatts on our supply. So that gets us our audio codec, feature extraction, and we're running active wake words through the neural network. And there's some neat things. We're a SPI connected peripheral, and we're going to tell you, fire that interrupt when something happens. On board, we have a holding tank. So we have, the last 3 seconds of audio that's happened, and it lets the system, essentially act like it's always been there. So you have a very expensive Bluetooth connection, right? These chips, 10 milliamps or whatever to get a Bluetooth live connection. We keep that completely shut down in your earbuds and wait for us to say something. And then when it happens, you can say, oh, no, okay, here's what the last 3 seconds of audio, and it can act like the connection was always there. So, we even provide this always on experience, but you can keep almost the whole system shut down with that.
Yeah, that's very cool. The economizing the RF that's what burns these little Bluetooth and Wi-Fi devices.
Yeah, that's right. I mean, the minute you turn on that radio, you got to get it off, and that's our job.
Cool.
But again, the Bluetooth they've set up for a couple hours of talk time, but 24 hours, you don't want this thing draining. While you're waiting for the moment that you have to make that important voice call. The battery's dead at that point. Then it's a miserable experience.
Yeah. Right. Okay.
So good. I mean, this is our 100. So what we call this our Syntiant Core 1 technology. It's like our first generation neural network, and it's all about this 500,000 parameter fully connected network. And we could train it to do some amazing things. What's on the market today? Our newest product announcement. This is the NDP120, and we're really moving into a much more powerful piece of silicon for inference at the edge. And essentially, Syntiant Core 2 is my teams and the ML teams have worked together to develop a neural decision processor, which is much more powerful.
Okay, and as I understand it, this is the one that's really targeted for the audio community in terms of it's adding some functionality of acoustic echo cancellation capability and things like this.
Yeah, exactly. So, three main things that we've done on this device. We talked to hundreds of customers, and we learned a lot with the 100. I mean, that's still going to be an amazing part for when power is absolutely, has to be the minimum. But with the 120, I mean, we really have, we've beefed up our audio side. So on the top left corner here, I mean, we have dual channel audio inputs, so we can handle PDM microphones, I2S, TDM streaming, and we have a couple more channels. So four microphone support, 4-channel I2S. We can actually be listening to 2 microphones and receiving a reference, playback stream on a second I2S stream. And that enables us to, this acoustic echo cancellation in the smart speaker. We can be canceling what's being played out through the stereo, still be actively listening to the microphones and provide that.
Oh, that's really cool. Yeah.
Right. It's pretty neat. And, again, we've seen that in the 100 because we only have, 3-wire interface. This, can plumb into an earbud like an ANC function. If someone has a high performance analog ANC, you can still feed that to our device and we can be doing, some of the speech processing and some of the later processing in this device.
Okay, so with that, just let me try to dumb this down. So that means that you could be using one path to pick up kind of, let's say, some of the defects of the speaker that's pushing out the sound while still maintaining the other input to hear for the wake words or the voice that it's looking for.
Yeah, exactly.
Okay.
Exactly right. And this is all set up. These are all DMA. I mean, the audio is automatically flowing through the system. The second main piece is we have a Hifi3 Dsp. So this is really what is enabling us to go attack audio and give us the flexibility to put in more, structured DSP type code. And so, the Hifi3 is a really good DSP at attacking these data path problems. So if I want to do acoustic echo-cancellation, there's filters and there's all kinds of spectral analysis. The DSP is really good at that. Big piece though, go ahead.
I was just going to say, and it's still able to maintain the low power threshold, because that's kind of one of the issues, I think, with the 100 is that you add the DSP and then your power balance in the whole circuit kind of falls off. Yeah,
that's right. And I'll show you what's fascinating. I mean, this is the big piece. I mean, we are really all in with neural compute. The Syntiant Core 2 is our neural compute engine. And so this is the part that's really powerful. So our goal fundamentally is to get audio in, let the Hi-Fi do some of the, the data path and structured and filtering problems. But as soon as possible, we're running stuff in the neural engine. And so we can do things like, look for the acoustic environment, to understand how we would change and tune the filters in the system. We can do, multiple mics into the Syntiant Core 2 to look for wake words, right? So that the wake word engine could be, with spatial information. It's all kinds of really neat things. Like we could even, there's all kinds of neural-based speech enhancement where, a trained neural network can do a much better job of analyzing the audio scenes and provide some coefficients back to the DSP for cleanup.
Okay.
So you look at it, pretty flexible, much bigger device. I mean, we've added some of the peripherals like an I2C controller and target. And so, this is the type of thing where in earbud, we could be doing sensor fusion because, we don't honestly care what is running in the neural network. The neural network is just as happy to learn audio and motion and do some kind of joint solution. Okay, bone conduction, this is in the ear and there's a lot of background noise, but I'm picking up the person's voice. You could do things like that to, even come up with a better outcome on wake word.
Right. Yeah, for wind noise or other kind of issues, like, again, back to being on the metro.
Right.
Yeah.
Yeah, and then, again, this is where we talk about, machine learning is, what kind of correlations are there, and you and I we can't see those. This machine with enough training data can see some pretty amazing patterns.
Oh, okay.
But, again, so I take this thing, and this is roughly 25x the compute of a 100 device. I mean, if you really want to pour on the performance and really run this thing, we have a lot of power on this. It's, close to 7 million parameters of neural parameters on this device if you push it to the 1-bit weights. But we have the flexibility, 1, 2, 4, 8-bit parameters. We can have flexibility in the types of neural networks that run on this device. And then what's more exciting, like what really gets machine learning teams here and the customers that we talk to, we've added things like fully connected convolutional networks, RNNs, LSTMs. These are, some of these recurrent neural networks that have time history are really good at some of these audio problems. So as opposed to just training, Syntiant Core 1, you can port your favorite networks. We're supporting all the types of the base components of machine learning that allows us to really do some really neat, vastly different architectures.
So does that mean if people are doing their machine learning modeling on these different platforms, it could translate into your device?
Yeah, that's right.
Okay.
Yeah, and then so we're not, we certainly are machine learning experts. We're developing our own solutions, but at any point, we can work with vendors. And, hey, if you have a good neural algorithm, we're happy, to open this up and put this on here. Particular, speech enhancement network, where it's open to map to our network.
Okay.
And that's it's pretty neat. I mean, this is the key thing is, the machine learning frameworks, again, like in the old days, you'd have to pay, thousands, if not tens of thousands of dollars for all this software. And the way machine learning has flipped it on the end, it's all open source. Like, here's the frameworks. It's the training data that's the key thing. So, we're able to support these open source frameworks and let customers train their own networks. What's really cool about the way that we designed this, designed it so that the chip teams, we manage every single bit. We're moving only the things that need to, but we present it as atomic layers. So in the case of an ML scientist, when they're in TensorFlow and training the networks that they want to use, that's going to embed right onto our device. So they're going to know the characteristics, the speed, the power of their solution well before it hits our silicon. And I think that's another difference, like a stored program, kind of DSP, MCU machine. You're running a compiler and you're running over and over again. Is it fitting? Am I missing my timing budgets? Like, there's a lot of hard work that we can avoid by the way we've hardened this device.
Okay, very cool.
So a couple of questions from me. Sorry, David, you mentioned TensorFlow a little bit. I'm not familiar with the term. Could you explain that?
Yeah, so I mean, TensorFlow is one of the frameworks out there that allows you to train machine learning. So there's some neat things. So you have to collect all this data, and you construct a neural network, and then you're hammering it with this training data. And you're just saying, yes, this is what I want. This is the right word. No, this is not. And through those millions of training epochs, the neural network starts to solidify parameters that lets it decide what you want it to do.
Okay, so you start with some inputs, and in advance what the output is supposed to be.
Yeah.
Yeah, and
you tell it, hey, this is correct. I'm going to give you this input, right? This is a WAV file with Alexa, and I'm going to tell you this is Alexa. So when you run it through the network, it reinforces that outcome. It says, oh yeah, you know what? That is Alexa. Why? And the machine has some training that says, why is that Alexa? Oh, I can see that. You're doing that millions of times.
Yep.
And then you're doing it with, this is not Alexa. So you do background noise and you say, look, hey, I'm going to send this to you. Guess what? Don't trigger on this.
Right.
And it's just an amazing thing. Gradient descent algorithms and these back propagation through very complicated linear algebra and nonlinear math that's supported in these frameworks. So it's an amazing, built on the shoulders of giants. So these frameworks are released.
When you use the term parameters, is that analogous to coefficients?
Yes, exactly. It's almost, it's a one-to-one. So one parameter is a coefficient
in that neural network. Yeah. And when you're talking about the training, over what period of time are we talking about? So you do some input and you have a known output, and then you do some algebra essentially to compute coefficients. It's like an enormous simultaneous equation to get all these inputs and outputs to line up. Is it something like that?
Exactly. I mean, so in these devices, so we're inference at the edge. So in the end, we train in the cloud. So prior to the release, we're running these on the cloud. We can do these GPUs, and so it can take days and days of training, and a week of training to get kind of the best production model. And I know you're gonna anchor that.
Yeah.
It's fascinating. But then what happens is you get into the field, like you think you've got the best network, right? You got 50,000 utterances, like, hey, this is pretty good. And then next thing you know, false accepts. And then what, the data advantage is if I can collect that feedback, you can roll that back in and you can get better and better at your task. So it's not even a static thing. With the right collection, these systems learn and they get better over time.
And so those, you've got layer types there. Are those a standardized format of coefficients? Is it?
Yeah, I mean, like
something like that?
convolutional is a kind of it's a well-known structure of, machine learning layer. And it's like a convolution would be, it's very similar, like convolution that you would think of in just standard math. It's like a small filter that you're sliding all over, some kind of features.
Mm-hmm.
And, they're efficient at the use of params because they get reuse. And it's very similar to the filtering of signal processing days. It's the framework, the way that we, hammer the coefficients, which makes the difference these days.
Okay. And so when you do the training, you come up with a set of parameters. How transportable is that into a device? So what I'm getting at is, do you need to train with the device mocked up in its final form, or is it relatively independent of that?
Yeah, it's relatively independent. I mean, we model, some of the microphone uncertainties, the transfer functions. Again, you would, we model the way the feature extraction is going to work on silicon is modeled in the training. So we would take that all into account. And of course, that's the real world is all about closing the loop between simulation and real world. So we'll train, and then we have our audio labs here. In Syntiant, I mean, we have rooms that have a HATS simulator, head and torso simulator. So we'll anchor that and go back and say, you know what, we think this is the model. Is that correct? And we definitely learn a tremendous amount to do that.
So I'm obviously coming from the viewpoint of, let's say, true wireless stereo earbuds with a microphone facing outwards, and the performance of that microphone is generally fairly flat. But if you had some oddity and resonance in there, that would influence the neural network's performance.
Yeah, that's right. That's right. We model those things. What is interesting about it is I'm trying to let, someone say a wake word in all kinds of dialects, male, female, like high pitch, low, slower, and things like that. So they're surprisingly resilient to a lot of things. Like you're training over kind of a wide range. So we would model that, say, hey, your earbud is slightly tuned and it's not directional, right? We would say, you know what, learn to understand the variation, be resilient to all of that.
So when someone's building a product, how do they get the set of parameters?
Basically, there's a couple of ways you can do that. So we a lot of customers will say, hey, I want to do some earbuds, and here's my wake word, right? We will just handle going and procuring all the data for that, new wake word. So we have that. We'll go collect the data. We will take the files, we'll clean them up, listen to them, have a whole team of people that will say, oh, no, this is good, this is bad, and work that through. We pump that through our pipeline, and that's where we can repeatedly rerun our structure with all our augmentations and get new inference for any word that you want.
Mm-hmm. Mm-hmm.
I mean, training is funny. I mean, it's the unsung hero of finding the right data and not letting bad data into your network. Because if you tell it something, it's not like it's smart and says, oh no, that's not Alexa, that doesn't make sense. Like, I trust what you tell me. So we had some glass break data where you can order glass break, and it turns out someone was breaking bottles and not windows. So what you learn is, hey, this network's going to be great at broken bottles and not in glass.
I suppose it depends on where you live, doesn't it?
Yeah, right.
So,
bar fight detector. I mean, someone broke a bottle, but it's not as good for other things.
What level of technical capability do your customers need to have?
Again, they in this particular case, they're asking for an outcome. Like, I just want this word to be detected. So you think about this. I mean, you look on our interface here. We're just a SPI peripheral. It's a very simple thing to drop into a platform and hide all the complexity in this neural network and say, hey, did someone say that command? Hey, get an interrupt. That's it. I mean, that's what, the Arduino and Raspberry Pi systems, there's millions of people that are dropping peripherals like this every day. Ours is pretty easy. We try and compartmentalize it. If you know what you're doing and you want, we're just as happy to open up the neural network and let you train your own, words. And we have customers that on both ends of the spectrum.
Sure. Okay. So then in that sense, then yes, if somebody's developing, not a particularly high technical skill, but they're developing a Bluetooth earbuds and they want to have this capability, you can pretty much drop the chip in.
Yeah. Yeah, right, exactly. And SDK. So we have our software development kit that allows you to just integrate it into any kind of limited processing element. So There's really not that much load, and we have all the software, that helps you drop this in. We have it for Android phones as well. So we've supported all those, and even the PC platforms. We have USB. We can integrate to that as well.
Use the term deep neural network a few times. Is that a grandiose way of saying neural networks, or is there a technical definition?
Yeah. So deep. The quick way to explain it is deep neural networks, and this is the power of neural networks, is not just linear algebra like big matrices, but there's a nonlinear element to it. And I think that's where traditional filtering and machine learning have kind of differed is that these nonlinear elements let this thing learn some pretty interesting slicing functions, I'll say. And deep neural networks is just I'm going to have 10 levels deep, 20 levels deep of these nonlinear choke points that allows it to learn things. And it's hard to describe, but deep neural networks literally is just, let's just stack up a very deep pipeline of these layers, and the machine, the data is flowing through these things, and it's given its power. And I don't know if the best analogy I can think of is like when I go back to communications, and you have QPSK and 16 QAM, and the stuff that the people know that go over the air with wireless communications. When you decide a bit, you slice it. You're trying to find a boundary that says, hey, is this bit 0 or this bit a 1? Machine learning is just doing that on a grandiose scale. So, 50,000 words are going through. It's trying to find a boundary that all of those words that I want to recognize are on one side of a boundary. All the other words I don't want are on the other side. And it's a really complicated, we tried to project some of them in, a 256 dimensional space of a boundary that the words are on one side and the other words on the other. It's really fascinating stuff.
Okay.
Next thing, the speaker ID, identifying who's speaking. That sounds like it differs significantly from a wake word type of a process. Is that on the architectural level much difference, or could you say something more about that?
Yeah, again, so speaker validation, identification, what you're doing is, you can train these things to answer to anybody for a particular word. And then, the speaker validation, what after the fact, there's some characteristics now that that the word has been said. There's some characteristics that you can learn with only a couple words of enrollment. So you as a person, have to enroll a couple utterances over and over again. So we can separate the problem. Hey, the word was said. I don't know who said it, but it's time for speaker validation to check, is it me that actually said that word? And so there are some of the features of the neural network that are available to help us, confirm, hey, oh yeah, actually it's the word has been said, so let's fire up the validation, and the characteristics of the enrollment match. So it's something we can train, the structure of that, and then we're not trying to just find that person to say the word. We're not training validation for looking for the word. We separate the problem.
Right. One small technical question on the first device, the NDP100, is it?
Yep.
It has a microphone input. Can that actually be paralleled from something else? Let's say you have Bluetooth earbuds with a microphone. Can you parallel that mic signal? Not exactly, right?
Yeah, well, so it's pretty cool. So the way that this works in the 100 and the 120 even is, the PDM digital mic interface is this, interface that you provide a clock, and you're going to receive this data on a left-right channel. What we've done in a lot of platforms is we'll drive the clock when the whole thing is asleep, right? So let's say we take a digital mic and we run it at 768 kilohertz. You know, we run low frequency. You know, we can still really get good quality audio for wake up. But when the system wakes up, and let's say there's a high performance processor that wants to run a really good high quality voice call, we're just as happy to tri-state our control of the microphone and turn it over to somebody else to take over. And that's the beauty of these digital mics. Like, I can share that with no additional circuitry just by tri-stating our control.
Right.
I'm happy for you to ramp this thing to 3 megahertz. You know, it lets you get 24-bit audio, high performance, audio, and suck that into your system. We can still passively, listen to that. We support up to 4 megahertz PDM. So if you're listening because you want high quality audio, I still with this device can listen and also pick up the audio if you want me to search for words.
Excellent.
So that's a pretty neat system.
Yeah.
And then in the 120, we definitely have some things like we can control dual microphones, and we can turn one of them off. We can control the clocks. So it may be that I don't always need dual mic, beamforming and spatial separation. I may just need one mic because there's nothing. It's quiet. I'm in a library or whatever. So we can always take advantage of shutting down microphones for low power as well.
And so that the Cortex M0 is a kind of a control interface for the host device.
Yeah, I mean that really is kind of it's an embedded device, and it really is kind of running our protocols like mailbox. We have a couple of semaphores that allow you to very quickly communicate with our device. The M0 is just internally doing some of those functions.
Right. But it's not available.
Hopefully, we try and keep. Right,
it's not available for the customer to put code on.
We try and keep. I mean, we keep this thing asleep as much as possible. It's just there to kind of handshake things.
Very cool.
Okay, that seems like quite a bit of information on this brand new NDP120, and this is excellent content. Sorry, Dave. Exactly what our audience loves, and exactly what Simon loves to dig in on. So
I appreciate it.
Yeah, so I guess if we have any more questions there, Simon, before we call it a day.
It's just say that when time's up, basically.
All right. So
So again, this stuff is all on our website. I mean, we can definitely follow up with us directly.
And
you guys will learn something.
I can pop. There's the website there. Everybody can see Syntiant.com, and we'll put all the social medias and stuff in the comments below, or in the description. Sorry. Anybody has any questions, just hit it up. I'm sure Syntiant's social marketing team will be checking for questions, and we'll forward them along as they come in. But yeah, once again, so everybody like, subscribe, and do all that good YouTube stuff. And thank you, Mr. Dave Garrett. Thanks for joining us today. We really appreciate it. And as always, Simon, thanks for calling in, and we'll see everybody next week.
Thanks, guys.
Okay. Bye-bye.
Yep. Thank you.